As in Y interaction with nickel-ferrum lead double hydroxide nanoparticles. Lead double hydroxide are materials structurally related to brucite, where some of the divalent metal cations are substituted by trivalent cations, resulting in a positively charged layer. This charge is balanced by anions in interlayer space along with water molecules. LDHs are of great interest due to their unique sorption properties associated with positively charged hydroxide layers and their ability to exchange interlayer anions. In this study, we used LDHs composed of divalent nickel and trivalent ferrum cations in a 2:1 molar ratio. The dominant interlayer anion is hydroxide. Nickel-ferrum LDH samples were synthesized via co-precipitation under a nitrogen atmosphere. We investigated the interaction of this LDH with diazine Y. Under our experimental conditions, azine is predominantly in its anionic double-charged form. We focus on three key aspects: the interaction parameters between azine Y and nickel-ferrum LDH, the type of this interaction, and the influence of azine Y on the hydrodynamic properties of nickel-ferrum LDH and aqueous suspension. To evaluate the loading parameters of azine Y and nickel-ferrum LDH, we conducted titration experiment using ultraviolet and visible spectroscopy. We processed the collected spectral data using the multivariate curve resolution algorithm, which allowed us to decompose the experimental spectra into contribution from individual components. This analysis generated distant spectra for three components: the LDH spectrum, and both the azine Y spectrum and the spectrum of azine Y adsorbed onto LDH. We also quantified their relative contribution to the total absorbance. The result enabled us to construct the isotherm of azine Y loading of the LDH, which we analyzed using the Langmuir absorption model. The loading capacity of LDH nanoparticles is typically described by two key parameters: encapsulation efficiency and loading efficiency. The studied LDHs show a high loading capacity for azine Y. Specifically, this phase of these LDHs can buy up to 91% of the 8 added azine Y. The amount of bond die can reach up to 25% of the total LDH mass. The XRT pattern of dried precipitate from azine nickel-ferrum LDH suspensions displays the characteristic reflection of a layered double hydroxide structure with well-defined basal reflection. It indicates that the layered architecture is preserved after azine Y loading. The overall peak intensity remains comparable to the pristine LDH, suggesting that azine Y incorporation does not significantly disrupt the crystalline order. There are no changes in the LDH interlayer distance, indicating that the azine binds to LDH through the phase absorption. Additionally, a small broad peak appears of the azine nickel-ferrum LDH sample, which may be associated with azine-related amorphous phases weakly interacted with the LDH matrix. The effect of azine Y on the hydrodynamic properties of nickel-ferrum LDH was assessed using dynamic light scattering and laser Doppler velocimetry. In the absence of dye, the suspension contains primary LDH particles with a hydrodynamic diameter of approximately 100 nanometers, corresponding to an equivalent spherical size. The colloidal stability of the suspension is primarily attributed to the high surface charge, with the zeta potential measured by the Haeckel method as 49 mV. Upon the absorption of azine Y onto the surface of LDH nanoparticles, we observe a gradual decrease in zeta potential. Initially, this decrease is minor, and the suspension remains colloidally stable. As the concentration of azine increases, surface charge neutralization occurs. It leads to a loss of colloidal stability. Nanoparticles begin to aggregate and eventually coagulate. Further, we see a recharging of nanoparticle surface, with the zeta potential dropping to around minus 45 mV. The particle size distribution shows that the suspension regains colloid stability due to electrostatic repulsion between the negatively charged particles. Summary: azine Y predominantly loads on nickel-ferrum LDH nanoparticles through surface absorption. Due to the high positive surface charge, nickel ferromaldehyde exhibits strong sorption capacity to what is in Y reflected in the high encapsulation allowed in efficiencies. As in Y absorption of nickel ferromaldehyde reduces the particle zeta potential and the colloidal stability of the suspensions. However, at higher zinc concentrations, the phase charge reversal occurs, restoring colloidal stability.